we now have Pavel Putrov that will talk about spin-cobordism, surgeries, and fermionic modular bootstrap. Please.
Thank you for the introduction, and also I would like to thank the organizers for inviting me to this event and to give this seminar. So my talk will be based on this relatively recent work with a student, Andrea Grigorta, who, by the way, will be applying for postdocs this fall. So let me begin with some motivation. And here in the beginning, I will be quite schematic and not very precise, but later on, I will make things more concrete. So suppose we fix our space-time dimension and some global symmetry group. Say B. And so what one can do, one consider kind of all possible quantum field theories in this given space-time dimension, which has this symmetry group. And one can consider a problem of classifying anomalies, including global anomalies of such quantum field theories. Suppose there is some formal set which classifies all possible anomalies. And so throughout the talk, we assume that the anomalies are in one-to-one correspondence with classification of anomalies is one-to-one correspondence with classification of symmetry protected topological states with the symmetry, the same symmetry G in +1 dimensions. So that the correspondence is given by the usual kind of anomaly in flow argument. So this quantum field theory is a theory which is can be defined on a boundary of an SPT. And more mathematically, by SPT, I will mean invertible topological quantum field theory, which has this symmetry. Okay. And moreover, this is not just a set. We know that this is actually forms an abelian group with respect to stacking operation. And what we can also consider the set of all possible representations of this group G, and consider a map between these two sets, so that physically this has meaning of taking a free. So if you consider some representation, we can consider free fermionic theory in this representation and consider its anomaly. And then another set which you consider is a set of all possible anomalous phases. Of let's say large diffeomorphisms and gauge transformations on a given space-time X. We know that anomalies exhibit themselves in particular. By the way, that if you put here on some space-time X and you do some, so it's the phase of the partition function in non-trivial background can be ill-defined, and in particular it changes non-trivially if you do large diffeomorphisms or gauge transformations. So, and this map is given by just putting this theory with given anomaly on some fixed space-time X. Okay. And so one can ask a question. So how to, okay, this is some general, very general things. So how do we, in practice, determine explicitly these maps? And again, this all these sets they can actually consider as abelian groups, whereas a group operation is a stacking of decoupled series together. And so why is this kind of interesting? Well, first of all, well, the kind of the first map is interesting. Is for example, if you ask a questions of, for example, anomaly cancellation or anomaly matching. So we are interested in kind of studying these maps. In particular, if you have a bunch of free fermions and different representations of some symmetry group, we can ask if this actually series, if this symmetry is non-anomalous, can we gauge it, for example. And of course, I mean, of course, this question is kind of non-trivial when these are global anomalies of, and when, for example, the symmetry group is discrete. Well, the other motivation is that comes from this kind of second map is can give you some constraints on possible values on how what kind of partition function of the theory can be. In particular, it can give you some constraints on the spectrum of the theory, for example, by using a modular bootstrap. Okay. Again, this is was just a motivation, and so let me mention another kind of a very kind of general property, which actually is kind of very relatively simple property, but it turns out to be quite constraining, in the purpose of determining these maps. So suppose we consider a pair of symmetry groups, let's say G and G prime. And suppose we have a group homomorphism F from G to G prime, so the map which respects the group law. So one simple example you can keep in mind is that the G is a subgroup of G prime. So, and then any such homomorphism between groups, it induces maps in the opposite directions for all these three groups here. In particular, I can write the following diagram. So we know very well, so if you have a map from G to G prime, this gives an opposite map between the representations of the corresponding groups. And similar thing happens to the group classifying anomalies. And why is it physically the case? Because we can formulate, like if the theory, quantum field theory has a symmetry group G prime, we can always formally consider also G as a symmetry of G prime by composing the action of G prime with this homomorphism. So any theory with symmetry G prime can be considered as a theory with symmetry G automatically. So this gives us this map. So let me clarify in my setup when I say that the symmetry has group G, don't require G to act kind of faithfully on the series. In particular, G can act trivially on all the operators if you wish. There's no problem with this. And similarly, we have maps in the opposite direction for anomalous phases. And then you have this commuted diagram, which is tells you that like if you go in any direction, the results should be the same. And this actually turns out to be, this is not just some formal nonsense. This is actually turns out to be very useful in practice to use this property. Okay, so let me now become more concrete and fix some things. So here in this talk, we assume that we have 1 + 1 dimension. So we consider quantum field series in 1 + 1 dimensions, or equivalently SPT in the bulk in 2 + 1 dimension, fermionic SPTs. And we consider the symmetry to be of the form, which is a product of the fermion parity Z2 times some global G, which is unitary and finite. So for example, you can keep in mind some examples. For example, G is something like Z2, or G is something like S3 is a group of permutation of 3 elements. But we want to develop some technique which works for any finite group G. And we also, for simplicity, assume that the series are absent of perturbative anomalies, because, well, it's very easy to deal with perturbative anomalies. In this case, the perturbative, when G is finite, the perturbative anomalies can be only gravitational. And when we consider a particular series on a particular spacetime X, we just take X to be a 2 torus. Okay, this is our setup. So what exactly in this setup, what are these groups, classifying groups in this particular setup? So by this representation, we will mean what is mathematically called the ring of real representations of G. So this can be defined as a kind of a group generated, a group consisting, an abelian group of formal differences. So we consider formal differences of pairs of representations where the representations here are real representations. So the representation vector space is a real vector space. And then when we consider the group classifying on all anomalies, this map is given by taking we take left moving fermions. Write in a different color. We take left moving fermions in row 2, and we also add the right moving chiral fermions, Majorana fermions in row 1. So we can have in this case in 1 + 1 we can have Majorana fermions. So we consider left and right moving fermions in certain representations, in certain real representations of G. And why only kind of we consider formal differences? Because whenever we have a pair of left and right moving fermions in the same representation, we can always give them a mass. So these the same representations, they always cancel out. So basically, this is a abelian group which is freely generated by all real representations. So what about the group classifying anomalies? So this is mathematically, as was proposed by, in particular, Kapustin and collaborators, and also later by Fried and Hopkins from mathematical point of view. This is so in the case when there are no perturbative anomalies, this can be described as the following group, which is a, well, let me write it down. So this is what can be called the Petrarchan dual to the spin-cobordism group of the in 3 dimensions of the classifying space of the group G. And so yeah, without going into details, this is well, basically some group which you can compute for given G. There's techniques. And well, what is kind of geometric meaning of this group? Let me very briefly mention this. So this is so elements here, they can be understood as U1 valued topological invariants of 3 manifolds. Which depend of 3 manifolds with G gauge bundle. So background, essentially, this is physically this is the background gauge field for our symmetry G, which depend only on borodism class. And the meaning of this is that we have a pair of 3 manifolds, let's say M3 and M3 prime, with some G bundles on them. And if we can connect them by some 4 manifold, so we can extend this G bundle across, then these invariants must be the same. So this is a very, yeah, here again, I'm not going into details, but this is a certain type of this borodism, you know, of the topological invariants of 3 manifolds equipped with this background G gauge fields. And so physically this, so the invariant is valid in U1, so it's a total phase. So physically this phase just means the partition function of the corresponding 2+1-dimensional SPT. Which we have in the bulk. Okay. And okay, let me for the moment consider just this part, and later on I will describe explicitly this the group which classifies anomalous phases and this map. So let me just give you some very simple examples. So which is quite well known. So
sorry, what is the U1 that you have there? This U1.
Well, this U1 is just a complex numbers with absolute value 1. It just doesn't. It has this many. It's just that if you have a, so we have a, so for each kind of anomaly, we associate a SPT. So anomaly in 1+1D. The in one-to-one correspondence in SPTs in 2+1D. And so if you consider the partition function of this SPT on this 3 manifold with some G gauge field. Here again, G is just some finite group. So this has a, because it's SPT, this always has a form of a total phase. Mm-hmm. And so this is a considered element of U1. So this is just, and this is a topology, it only depends on topology of a 3 manifold and the topology of this bundle. That's just this meaning.
That's not the partition function.
Hmm?
It's not a partition function.
It's a partition function of a bulk SPT, not the partition function of the boundary. Yeah.
Shouldn't be real.
Why? No. No. This is real when this has some sort of if this has some reflection symmetry, then this is real. But in general, it's a phase.
Okay, go on. Then maybe we return later on this question, please. Another question. What is BG?
Well, BG is a classifying space of G. So it's so we consider so if we have some space-time let's say, well, here, yeah, so here we're talking for the bulk space-time. So it's a three manifold, and we consider, so the statement that if you, so for a group G, we can associate some topological space BG so that if you consider all possible maps from three manifold to this BG, so this the set of all such maps up to homotopy, this is the same as the set of isomorphism classes of principal bundles. But you can understand this the whole thing. Yeah, the whole yeah. The point is that you can understand the whole. So what is this group? So here you have a pentagon of this group like this, and this group you can understand just as a group where the kind of is generated by equivalence classes of three manifolds. So what is this group? So this can be understood as a three manifolds with G bundles up to equivalence relation. And equivalence relation is what I mentioned earlier, so that the manifolds with G bundles are equivalent if they can be connected by a four manifold. And the G bundle can be extended along this four manifold. And here, yeah, I shouldn't have mentioned, but yeah, I'm assuming everything is Euclidean here. Any other questions? Okay, yeah, let me give you some simple example. So this was quite like formal in general, but yeah, in practice, yeah, the point is that yeah, this is some group which one can calculate by different methods. In particular, there is also equivalent description which is called supercohomology description, which can understand this group in terms of more ordinary like group cohomology theory. This gives you more algebraic description of this group. So if G is equal to Z2, for example, so this the group which classifies anomalies into dimensions or equivalently SPTs in 3 dimensions is known to be Z8. And so what is this ring of real representations, which we actually only consider as a group? So this has the only two irreducible representations of Z2. It's a trivial representation and sign representation. So they're both real one-dimensional representations. So one is, in other words, this is a 0 charge and this is a charge 1 representation. So this group is Z square is just free and group with 2 distributors. This means we can consider chiral fermions. Effectively, it means that we consider chiral fermions in trivial representation and sign representations. And so this map to the 8 is given as follows. So we take, suppose we take a fermions, chiral fermions in trivial representations, A fermions in trivial representation, B in sign representations, and the result is just B mod, the value of B mod 8. And this corresponds to a physical fact that if you have 8 fermions, these fermions can be gapped in groups of 8. Yes, anomalies in 1+1 dimensions or SPTs in 2+1 dimension. And yeah, the symmetry is fermion parity and Z2 unitary symmetry. No, this part I'm not considering any particular space-time so far. This will be for the torus will be yeah, the later I will consider. So this is anomalies which kind of not related to any particular space-time. So yeah, this is a result basically which goes back to Ryu Zhang and Gu Levin, who showed as a corresponding. Well, I mean, this comes back to well, Ryu and Zhang, yeah, I think 11, and Gu Levin. Well, I mean, they didn't use the cobordism description or whatever. I mean, it's just a result that if you can gap, essentially result that you can gap 8 groups of 8 fermions together. It's an example of this map, how we kind of go from the if you have a bunch of fermions in given representations, how we determine the value of its anomaly. So we know in particular, so if this is, so suppose there is a question of, we start with some fermions in some representations, and we are asking, with respect to some global symmetry, and we ask the question, can we gauge this symmetry or not? So in general, we want to study this map. So when this the result is 0, if the result is 0, then we can gauge it. So here we learned that only if this B is 0 modulo n, then we can gauge the symmetry.
I know, because I can write an interaction that maps that give a mass to these 8 fermions, yes. But is this also a result of your analysis, or you take
no? This is just example. It's example where you don't need this analysis. But,
okay.
This is example which is well known.
Okay.
It was well known before.
Okay.
And now I now sell something which one can use in general.
Thank you.
For general.
Thank you.
So now we want to consider some general finite group G. And study this map from again, this is a big group just freely generated by real representations of G, and this is some group classifying anomalies. And again, mathematically, it's given by this contragin dual to the spin-cobordism group. And so let me so let me note it by this map by G2. So this has some sort of similar meaning to second component of the Chern character, which is a similar map, kind of, which determines this map in the case when we study perturbative. And so I also probably should mention that this map kind of, if you use what is called super cohomology description of this group, so this gives you a certain kind of split this into some components, and some components of this map they were analyzed previously in the paper by Chen, Kapustin, Turzila, and you. But yeah, I want to take a different approach and I want to make the following, which is kind of based on some.
I'm sorry again. Maybe you shouldn't use the green. That maybe is not very well visible. Just to use white, please.
Okay. So I want to make the following claims that this can be, so this map can always be fixed by the following what one can call axioms. Which, well, this is a property of this map which has a physical some physical meaning. So what is these axioms? So first is linearity. So you say that if you take a sum of two representations, the value of this map is a sum of the values, and this basically means that the behavior, so the anomalies add up when you stack series of free fermions. And the second property is naturality. Which means that if you consider any group homomorphism from G prime, then the following is true. That, okay, so if you have some representation of G prime, this gives us the representation of G, which is called pullback representation of R, and denoted F star of R. But similarly, if you have some anomaly of for the group G prime, as I mentioned before, we can consider pullback map. So we can consider pullback of anomaly. So this is something which is valued in A of G. And the third property is can be called normalization. Is that for all abelian G, the values of this map, which is denoted by G2, are given. And this is essentially tabulated in our paper. Right? And this is more or less collection of results which were previously known plus something new tabulated in the paper. So essentially, there is a paper in our paper. We kind of there is a table. So for any abelian G, what is this A of G, and what is this? How to determine? So for any abelian G, the representations are easy to describe. They're essentially given by some charges, and one can explicitly describe this map for all possible abelian Gs. Okay, so so let me give you an example how one can use this. Again, I'm not going to give a complicated example by something similar, something rather simple. So suppose we consider as a group to be S3, so the group of permutation of 3 elements. And one can consider the following homomorphisms to and from this S3 and some abelian groups. So this is so we have a map from Z2 to S3, which is just gives a transposition of 2 elements. And this map from S3 to Z2 is given by parity. So we just consider parity of representation. And this inclusion of Z3 into S3 is can be understood as a subgroup of cyclic permutations. This is kind of a diagram of possible symmetry groups. And respectively for each symmetry group, we can calculate the group which classifies anomalies. So in this case, the anomalies are classified by Z8. Here it's also Z8. And for Z3, one can show that anomalies are classified by Z3. And for S3, one can show that anomalies are classified by Z8 times Z3. And the maps between the anomalies, the groups classifying anomalies will be in opposite direction. Because again, for example, if you consider this map, the symmetry, the series with anomalies with symmetry group Z2, it can be understood as a symmetry, as a series with symmetry S3 by just kind of where S3 acts here only by parity. And in particular, we know that this, for example, this composition is just identity. So this is also must be identity. Yeah. And so using the fact that we know how this map, which determines anomalies of free fermions, works for all abelian groups, we can determine this map for S3. In particular, the result is the following. So for S3, we have 3 irreducible representations. So one is trivial, the one-dimensional real representation. The other is sign representation, which again, so we have just one real fermion which flips a sign depending on the parity of this permutation, and there is non-trivial two-dimensional real representation, which is so you act on a pair of real fermions as so you consider this kind of the space of two fermions on a plane, and you consider this S3 as a group of isometries of a equilateral triangle here. Okay, and so okay, you have a group classifying anomalies is Z8 times Z3, and the trivial, of course, goes to 0 and doesn't give you any anomaly. The sign the sign representation goes to 1, 0, and this non-trivial two-dimensional representation goes to 1, 1 element. And you can use the same technique for more complicated non-abelian groups. Any questions? So how much time do I have? 10 minutes? Okay. Okay, so now let me mention briefly about the second part. So what happens when we put a theory on a particular space-time, and what part of anomalies are captured by these anomalous phases which appear under, yes.
So to determine these maps by the 3 axioms, you're using the data that you know what they are for the abelian groups.
Yes. This is some non-trivial. Well, this is partly what's available in the literature, partly this is some new calculation.
Okay. Yes. But in addition, don't you need to know how to do these homomorphisms between abelian groups and the non-abelian one and so on?
Yeah, you need to know how to essentially calculate this F star.
Okay, so
F star from A. So if you have F from G to G prime, yeah, you need to know how to calculate this map between the groups of classifying anomalies.
Okay. And you could also have different, could you have different Fs, for example, for?
Yeah, usually you need to consider different. So you start with G and you consider different.
All possible. Okay.
Yeah, yeah,
okay.
in and out. So you need to consider all in and out. Yes.
Okay. So
I mean, more complicated cases, you may need to consider some kind of even some sequence.
Okay, so as data, you need the Fs as one for the calculation. To complete the calculation, the data needed is 3 axioms plus knowledge of what F is.
Yeah, you need to know how to use this F star here.
Thank you.
Yes, and this can be, for example, like if one uses, it can be, for example, used if one uses this super cohomology description. One can, in terms of when one describes this in terms of some group cohomology, one can, basically one can describe this F star in terms of super cohomology in some algebraic way. So, okay, what is the kind of mathematical data which describe anomalous phases? Well, on particular on T2. So for each choice of background on a torus, and so the background is, so let me introduce this notation, spin G of T2, which is essentially the space of all possible backgrounds. So this is just a space of all possible spin structures on a torus. So there are 4 different spin structures, and the space of all possible holonomies of my group G on a torus. So here, basically, the first part means that we have to specify periodic or anti-periodic boundary condition on the fermions for each cycle. And here, we have to specify a pair of elements of the group which commute itself. Which, yeah. So GI is element of G. So it's just holonomies. Okay, so for each possible background, we associate a one-dimensional Hilbert space. And so let me choose a basis here. So there's just one basis element, A. And so physically, again, this is the Hilbert space of the of this 2 plus 1 dimensional SPT. And from the point of view of the anomalous theory in 1 plus 1 dimension, the partition function is not a number, but it's actually an element of this. So there's an element of this one-dimensional Hilbert space. And for each element G in, so we consider the following group, which describes, sorry, maybe it's better to introduce some other notation. Let's say H. We consider the following group, which describes large diffeomorphisms and large gauge transformation. So group of large gauge transformation is just a copy of G itself, so this is so the usual group of large diffeomorphisms for torus is SL to Z, but here, since we're considering a tori with spin structures, we have to consider its what is its certain central extension. So this is what is called a metaplectic group. This is a central extension of the usual modular group SL to Z by Z2, which has a meaning of fermion parity. And in terms of generators, so this is a group generated by S and T with the following relation. So one is the relation as usual, ST cube equals S squared, but instead of S to the 4 equals 1, we have S to the 4 equals to minus 1 to the F, whereas this is some element for order 2. And so for each H, we have a map for each H of this group, which describes large diffeomorphisms and gauge transformation. We have a map between the corresponding between these Hilbert spaces. In particular, we start with some Hilbert space where the basis with this corresponding to background A, it goes to, so we go to this space where with background changed by H. So this is a group. So we have elements of this group, they act on the set of possible backgrounds. So this changes background, and this possibly gives you some phase, which is depends on what background we started with, and this element of this group. And for consistency, this should have satisfied the one cycle condition. And so such data up to change of basis classified by a certain first homology group. Essentially, is a kind of the set of these functions up to change of basis. So the H1 of this group, which we have here. And so the coefficients are U1, so for each background, we have a copy of U1. So it's a U1 to the power spin G of T2. Okay, and so let me denote it by, let's say, 5G. So again, this is a group which classifies all possible anomaly spaces, which are just consistent with the kind of group action, with action of the large diffeomorphisms and gauge transformations. And then we have so this map from the group classifying anomalies to this group classifying phases. And so in general, this map actually is neither surjective nor injective. But in some simple cases, you can capture all possible anomalies by considering different phases. But in general, this is not true. And okay, so I have to wrap up. So the point is that, okay, so let me just make a brief summary of what we did. So, so one can so okay, this is map. So the point is that one can determine this map explicitly. And so what are the steps here? Essentially for general G. So first argument that the case is kind of reduce. You can reduce the problem to abelian groups. So you can argue that the case of the general G can be actually reduced to the case of abelian Gs. And second part is that we can so the map, so this the value of this star is actually determined by the values of the values of SPT partition functions on certain closed three manifolds. And the third step essentially there is a combinatorial. So we present a combinatorial way. So if three manifolds can be represented combinatorially using what is called surgery. And in terms of this combinatorial data, one can provide a method to calculate this the partition function of SPTs for abelian G using these combinatorial surgery descriptions. Determined, so these values, again, geometrically, these values of partition functions dimensions, there's a certain topological invariance. So these values can be determined using combinatorial surgery description of 3 manifolds and background gauge fields. Again, so yeah, like for general abelian G, we provide explicit formulas how to calculate the partition functions on any essentially on any 3 manifold using the surgery representation. And so this so in particular the result can be used to do modular bootstrap. So we do this in this paper. We do this when G is just again Z2. But yeah, the student Andrei Guralev is actually working on some generalization for other G's. And but for G equals Z2, so the result is kind of so what you can do, you can find some kinks in well, which essentially can be realized by some free fermions in certain representations. Okay, sorry about going over time. I stop here.
Let's thank the speaker. Do you have questions?
Is there a question on Zoom?
Emanuele, you have a question? Okay.
No, this is just
that's the hand. No,
just a pointer.
The reduction to abelian groups that you mentioned here, that's still for T2, right?
Yeah, this is yeah. Here the T2 is important because essentially we're using the functions. This is
so those two can be
this is but again, like for fixed non-abelian G, we have to consider different we have to consider different abelian subgroups.
The homology is usually commute because the homology group is commutative, right? Because it's a torus. Isn't that the relevant issue for the for reducing this to the abelian groups? Is that what you're using?
Well, yeah, in this yeah, when I reduce the abelian group, I essentially use the fact that on a torus, I have to pick this community. Yeah, those community. I'm using this fact. Yes.
Just want to make sure that
yes,
that's where it comes.
Yeah.
I see. Thank you.
More questions? Okay, then we thank the speaker again, and we have a break of 5-10 minutes.